So should I get started? Okay, should I get started?
Sure. I guess I'll introduce. So this is Karthik. Karthik's got a PhD from the University of Michigan. He's now a postdoc with Peter Fox at the University of Washington. And, go ahead. Yeah.
Yeah. Hi, everyone. First of all, thanks to the organizers for the invitation to present my research. And today I'm going to be talking about the recent research efforts on learning object-centric representation for robot manipulation. And I believe this is very relevant to the theme of the workshop. And so this work is done in collaboration with Ventau, Chris, and Dieter. So let's take a look at a particular task here. So consider a rearrangement task where the robot is given a goal configuration to achieve. And here is a snapshot of a particular point during the execution where the robot is holding a blue block, and the planned action is to put the blue block on the red block. So I'm going to be talking mostly from the perception side of the problem here. So if we enlist what a state estimator might have to do to inform a task and motion planner, the simplest thing one could think about is to find what objects are in the scene and where they are. This would be object detection. And let's say the next thing that one would want to think about is the robot has to reach out to these objects in the scene and perform grasping actions. So this might involve knowing where the location of the object is in terms of position and orientation, which is the object pose estimation problem. And now, depending on the complexity of the environment and the task itself, one might want to find a relationship between object and the semantic locations that are involved in the scene. So here, a simple question could be, is the block held by the robot, or is it actually in the far end of the table or in the center region of the table and so forth? So considering the specific task here, let's say it's a rearrangement task, which involves stacking and unstacking of objects, it is also essential to know inter-object relationships. For example, is the red block free enough to actually support the stacking of the blue block? Or is it actually supporting another object at this particular state? So overall, the state estimation can be very complex depending on the task and the scenario. So if we take a very traditional approach, one way to do this would be to build a state estimator by weaving all these multiple modules that can output all the relevant information for task and motion planner, right? However, there are a lot of drawbacks here. One thing, to do a pose estimation, you would require a 3D model of the object. And it is hard to generalize the setting to new unseen object instances. And especially given that this is a rearrangement task, where the objects are in close contact with each other, the initial failures from the other modules could actually result in catastrophic failure in the actual task itself. So one way or the alternative approach that has emerged in the recent years is to actually train a neural network and do an end-to-end learning where you can actually convert an RGB observation into motor policies. So this actually abstracts all the information and does an implicit state estimation internally and directly outputs the motor commands. However, the criticism and the drawbacks of this work is that it is optimized for a single task or a goal, and it does not explicitly reason about spatial relationship between the entities in the scene. And because of that, it does not generalize to different task configurations that involves different objects. So what we are trying to explore is a space that is in between. So in the spectrum of approaches between modular and end-to-end, we are taking a middle ground where we are saying that, okay, let's do state estimation or perception, where a pre-trained model can learn an implicit representation about physical objects in the scene. And it can output object-centric embeddings whenever queried for robot manipulation tasks. So this is the approach that we are trying to explore in this research. And the desired features for this approach are like, let's not have a dependency on a 3D object model. And let's see if we can generalize to unseen object instances in a zero-shot or a few-shot fashion. And being able to have compatibility with different task scenarios is one of the desired features as well. And most importantly, for all of these tasks, we believe the object embeddings should capture spatial relationships that are both continuous and discrete in fashion. So to do this, we are inspired from the advancements that's happening in NLP and computer vision literature. So one of the recent some of the recent works have shown that you can do powerful embedding learning with weak supervision, let's say using internet data. And also we have seen that a lot of efficient self-supervised learning methods have been proposed that combines language and visual data, especially if you have not seen some of the works like CLIP, BERT and stuff, you can actually see that they produce shockingly good generalization in recognition tasks in a few short manner. However, in robotics, we should also think about the fact that robotics is a complex domain which involves robot control and actions that actually change the world. Moreover, it requires accurate spatial reasoning. Sorry. And we do not have enough data for all of the tasks that we would like to approach for. And we do not know what is the right supervision to actually have this translate to robotics domain. So having said that, we are taking a step towards addressing some of these issues while leveraging the advancements in NLP and computer vision. So with that, we propose or present our first iteration to the middle ground approach that I was talking about. So we propose SORNet, which is a spatial object-centric representation network that learns to output object-centric embeddings, which encodes spatial relationships. So the key idea here is that SORNet learns object-centric embeddings from raw RGB observations. And the way we want to figure out how good these object embeddings are is by looking at demonstrations that says that learning these embeddings can actually avail for doing spatial relationships on unseen objects in a zero-shot fashion. And it can also be used for classifying skill preconditions that are relevant to robot manipulation tasks. And we are also able to say that with the large amounts of data, the embeddings can actually capture continuous information in the form of relative direction between the physical entities. So let's look at how the SORNet works. The input to the network is an RGB frame and a set of image patches, which we call canonical views. Note that these canonical views serve as queries to the network. So we can actually query for any object of interest saying, okay, can you give me an embedding for that? There can be any image of the object, which need not be part of the current scene in the input, current input frame. In addition, during the inference, you can imagine that only one canonical view of an object would be sufficient to actually query for that particular object. So SORNet first splits the input frame into context patches, concatenate them with the canonical object views. The sequence of image patches are then linearly projected, flattened into a sequence of vectors. And this sequence is added with positional encoding, and it is passed to through a transformer, which is multi-layer, multi-headed. And we are using a VIT transformer, which is a vision transformer network for doing this. And the tokens in the final layer of the transformer are corresponding to the canonical views of the objects. So the interesting thing to note here is that this network is very flexible, that you can actually query for a subset of objects in the scene. So for example, in the scene, we have 4 objects. You can query for 1 to 4 objects in the scene, which would give embeddings for each of these query objects. So the way we are training this is to actually do predicate classification. So the predicate classifier consists of two layer perceptrons, each corresponding to a type of relationship. So the one that is highlighted here, which is basically unary perceptron, that basically predicts logical states involving single object. For example, here, the questions could be, is the object blue on the surface, on the left surface of the table? Or is this object being held by the robot? Or is the top of this object clear for potentially a place action? The other type of predicate statements would be involving pair of objects. For example, here, we can say that is object A stacked on top of object B? And we can also ask the question saying, is it actually aligned with the object before a place action? So you can think about these as a collection of predicates that talks about spatial relationships, as well as logical states that talks about the preconditions that are necessary for a particular task. So as shown here, you can imagine that the network is flexible to actually account for different number of objects in the scene. So, so we do not actually constrain to number of queries and the number of predicates that we can output from this network. So the training data for this approach is being generated in simulation. A large data is generated with thousands of sequences where the robot is performing a sequential manipulation task. And we use domain randomization in rendering the observation, so this can be used directly from sim to real for sim to real transfer. To test the generalization that I talked about, our training data has 405 colored blocks, while the test data has only 7, which is not part of the training set. And the training data is very simple sequential task where you always have 4 blocks randomly chosen from the 405 color. And with the task being where the objects are on the table, and it goes from completely unstacked state to a stacked state. Whereas during the testing scenario, we have 7 different goals that the robot has to execute, which could be a subset of stacks, partial stacking scenarios, and so forth, involving different regions of the table. So before even looking at so I'm not going to talk about how the performance is on the simulation data. So I want to jump into the real world experimental setup here. So this is a real world experimental setup where you have 4 colored blocks that were not seen during the training. And we use the same Franca arm that was part of the simulation data. And as I said before, the table is basically divided into 4 overlapping regions. And this makes the goal conditions a little complex, involving stacks of objects required to be at specific locations on the table, or specific regions on the table. So let's see in action how the predicates that were predictor classified by the StarNet can be used for this particular setup. So as I said, you have an input frame, and then we are asking for object embeddings that are coming for these specific set of objects. So in the screen that you see, the predicates predicted are the true, are the predicates only corresponding to the true values. So there are 54 predicates for this particular experiment. I'm only listing the ones that are true. And the goal conditions, as you can see, which says the robot should not have anything in its hand at the end of the task execution. The green block should be on the table, and the green block should be supporting the yellow block, and the red block should be on the table while supporting the blue block. So this is a goal condition, and this is the predicates for this particular state of the scene. So with that, we can actually use these predicate values to generate a plan using a symbolic planner. And that gives us a list of actions the robot has to take to actually reach the particular set of goal conditions. So we do this in an open loop fashion at this point, where we can say using the states that was predicted by StarNet, we are able to do task and motion planning to perform a particular task. So let's look at another scenario. And again, to just mention the setup, whatever you're seeing on the left side is basically recorded from an external camera, and the observations are coming from the sensor that is behind the robot. So this is a different scenario where the goal conditions are slightly different, and a plan is generated followed by the robot execution. So to be very clear, so we haven't done any fine tuning on the real world data or the observation. It was completely trained on the simulation environment, where it has not seen these 4 colored blocks. It has only seen other colored blocks. So the idea is to make the framework as general as possible so that you can query for the objects of interest that is specific to the particular state or the scene. Okay, so in addition to this, what we have seen is that SORNet is able to capture not only the discrete spatial relationships, but also continuous spatial relationships. So here we train a regressor on top of the frozen SORNet embedding. So SORNet is trained with the dataset I spoke about, and it's frozen. And we are saying, okay, can you use these embeddings to actually predict a 3D unit direction, a scalar distance between robot's end effector and the center of object. So we can also do this between any entities in the scene. But for this example, we are just showing how we can use this predicted direction and guide the end effector towards target object using a position control. So to repeat what I said earlier, SORNet embeddings capture continuous 3D spatial relationships between entities, although it was never trained on any metric task. So it was only trained on the predicates that we saw earlier. So we see that the work that we are doing is related to the visual question answering domain of research. So we tested how good the spatial relationship prediction is on a VQA dataset. So specifically here, Clever Cogent T dataset, which has 4 different spatial relationships that talks about whether an object is left off, right off, in front of, behind of the other object. So the reason we chose this dataset is it has 2 splits where, for example, if I have to point out here, the objects are not repeated, or they are not part of, they're exclusive in terms of the split. For example, if you look at the red cylinder, you don't see the red cylinder in the condition B, but you see it in condition A, whereas in condition B, you see a red cube. So with this, we are able to say that if you train the SORNet purely on, let's say, set A, and without even looking at the set B, as long as you can pass the query views of the object that you care about, you can perform, we can perform really well in terms of the prediction accuracy. So let's look at some examples. So here we're saying, is the small cyan metal sphere to the left of large red metal cube? So this is the object views that we provide for the SORNet. So SORNet does not do any language parsing at this point. So it's only using the object views to actually guide which objects that we are talking about. So the other example in the same setup would be, is a small brown rubber cylinder to the left of large gray metal cylinder? The answer is no. And the way we are trying to disambiguate in terms of scale, so this data set has the adjective that talks about like small, medium, large, and so forth. So the way we are disambiguating that for SORNet is to give the object views that are already scaled. So it has a scale difference between 2 objects in terms of this size. Here is another example. So is the small brown metal cylinder behind the small green metal cylinder? And the predictions are no. So we compare this with the state-of-the-art method MDeter, which is also using zero-shot learning to predict these, to give these logical states. So in conclusion, what I spoke in the past 15 minutes or so is that what do I mean by object-centric representation in the context of robot manipulation, especially long horizon manipulation tasks. And I spoke about a specific instance of the approach, which is SORNet, that that came out of a group, which is spatial object-centric representation network. And what we are able to show is that it generalizes to unseen object instances, specifically blocks in the robot setting, as well as instances that are different shapes in the clever cogent T dataset. It supports generalization to new tasks because of its because we are still using the task and motion planner for generalizing across new task scenarios. And it transfers well from sim to real. So as I said, we only trained on the simulation data and readily use it on the real world to predict the states of the scene. And finally, it is trained on logical spatial predicates, but it can also capture continuous spatial relationships. So while listing out all these positive things about SORNet, we are not perfect yet, right? We are still like trying to push this direction and see how much we can go. So the next iterations that we are looking at would be objects with complex appearances and shapes, and testing the limits of generalization to new objects that are beyond blocks and complex place locations that are beyond tabletop environments. And we also want to test the limits of continuous spatial relationships that are being captured by SORNet, because we feel that that could be used for an RL-based approach. So with that, thank you so much for giving this opportunity. I'm happy to take any questions.